Okay, today we're going to talk a little bit about structural geology. And so for this class, what that's going to involve is looking at two of the main features when it comes to structural geology, and that's going to be folds and faults. So of course on this image here, you can see some examples of those. Some of these structures can be fairly large, regional kind of folding. Others can be very small, as you can see by the image to the left there with the pen as a reference. And so what we want to do is just going to go through some of the techniques we use to identify these structures in both a map view, where we're looking from the surface of the earth, let's say looking down from your airplane, or in a cross-sectional view, which is a side view. And you can think of that kind of like a road cut, where we cut through the rocks and we're able to see at depth. So a couple things we want to talk about first is what causes these things. And so rocks can be put under stress, so we know that from talking about plate tectonics. This is one of the probably the best places and sources of the stress that rocks get exposed to. So we know that there are convergent boundaries, divergent boundaries, and transform boundaries. All of these are applying some type of stress to the rocks. And if we stress out the rocks, they can become deformed. So when we talked about, let's see, what did we talk about? We talked about geologic time and relative age dating. We talked about sedimentary rocks and how they are deposited in a horizontal position, kind of like the image to the left there. And so this is what we'd expect when sedimentary rocks are created or formed. What we can see is that at times we find rocks that have been put under stress, and then they have been altered from their original position. And so in this picture to the right here, you can see that the rocks are no longer horizontal. In this case, they have this curve, this tilt to them. And as a geologist, when you're out in the field, this suggests that the rocks have undergone some type of stress and they have deformed. So if we can identify the type of stress, the type of structure, it gives us some information about the history of what occurred here. And we talk about that, that's kind of something that we're interested in for geology, is the history of what occurred. And also, we have to remember that a lot of these structures, if they're, of course, a fault, they have some impact on society. We know earthquakes would occur there. That's something we might be concerned with. Structures, like the one you see on the right where the rocks are curved, they tend to actually trap some resources for us, in particular oil and gas. And at least currently, that's something that we're interested in. So identifying these structures doesn't just lead to, stories of what occurred here in the past, but also of what, might happen in the future relative to earthquakes or some resources that we can acquire. So we want to show the different types of stresses that can be applied to the rocks. And once again, we want to bring this back to the big story of plate tectonics. And so here is a diagram just illustrating the different boundaries that we've talked about, right? We have compression, which is what you see in this first little diagram here. And so here where the rocks are being crushed, and we would say that we could see that in some type of convergent boundary, right? Over here, where two plates are colliding. And in this case, it doesn't matter if there's subduction or not. It's just that stress. That stress is going to deform the rocks in a specific way. We want to be able to identify the stress and the structure, or the structure and the stress. The second type of stress we want to talk about is what's called tension. So that's just the opposite, of course. Here we are pulling the rocks apart. We would say that if we had to pick a plate boundary to associate that type of stress, we would look at divergent plate boundaries where the plates are being ripped apart. And so tension is occurring there. We get different types of structures there. And finally, our third type, right down here, shear, is when the rocks actually are sliding past each other. And so an example of shear stress would be occurring at a transform boundary. And so part of what we want you to do when we're looking at stresses and structures is also understand the probable plate tectonic boundary where those stresses would occur and also those structures would occur. Now, like everything we talk about in geology, these things are not absolute. So we can't say 100% you always get this, this, and this. But in general, those statements are true. Compression is what we're seeing in convergent boundaries. Tension is what we're seeing in divergent boundaries. And shear stress is what we're seeing in our transform boundaries. All right, what else do we got? So there's a couple different ways we can form our two different types of structures. And so what we want to say is that when rocks are put under stress and they behave in a brittle fashion, they're going to break, like we see on the left here. When rocks are put under stress, they can also fold or bend or fail in a ductile fashion, which is what that word means, kind of like a plastic deformation where we can kind of bend things instead of breaking them. And so there's a couple reasons why this might occur. And if we look at some of the properties that lead to these different types of failures, you see that in general, rocks that are colder, so have a lower T or lower temperature, the rocks are very strong. And if we're applying the stress and the strain is happening very quickly, those tend to lead to brittle failure or faulting. Where on the other hand, the folding aspect, if the rocks are hotter, if they're weaker, and of course if the strain, the changing rate is slower, you have a better chance of folding the rocks. And probably the big controller here is going to be the temperature. What we see is that rocks near the surface are cooler, and when they undergo some type of stress, they tend to fail in a brittle fashion, so faulting tends to occur near the surface. And of course, deeper in the earth, where temperatures are higher, rocks can have the ability to bend under that strain under that stress, instead of breaking. Now, of course, how do we get these folds to the surface so that you can actually see them? If we're saying that they are occurring deep in the earth, well, we know how that can happen. We argued that how do we bring igneous rocks that are cool inside the earth? We said granite has really big crystals. Those things cool deep in the earth, maybe 5 kilometers deep. How am I able to see that at the surface? Well, we know that uplift occurs. Once again, we can bring that back to our plate tectonic story. We have these big collisions, uplift, and weathering and erosion is stripping that material down until I can expose some of these features that form deep in the earth. And that would be true of our folding. So, how do we know that the rocks have been deformed? I kind of mentioned this a little earlier, but what we want to remember is sedimentary rocks here are the key. So metamorphic rocks and igneous rocks don't always have this indicator of change, whereas sedimentary rocks, because they're deposited in these layers, and the layers are horizontal, any change from their orientation of being flat is an indication that some type of stress might have occurred here. And we want to look and see have the rocks been faulted or folded. And so certainly a good indicator near the surface as we're hiking around is that when we see tilted beds like this, for sure something has occurred here. Now, these tilted beds might be part of a fold. They also might be part of a fault, because when we break the rocks can get tilted in addition to moving across some fault plane that we'll talk about in just a little bit. But of course, as just a general rule, you're out hiking and you see layered rock that has been tilted, right? Not horizontal anymore. It's a clue. And then you want to, of course, do some more investigation. Hopefully you'd be able to figure out that there has been either a fold or a fault, and then we can gather some more information about those structures. So, how do we describe this change in orientation? So, a concept we want to introduce to you, and you'll see this in your lab also this week, is what's called a strike and a dip. So a strike and a dip, they are measurements of the orientation of this tilted layer that you see. And so the strike is actually just the compass direction. So what does that mean? Well, it means if I look at my compass, I could say that the layer that has been tilted has a strike to the north, or it might have a strike to the east, or it might even have a strike to the northeast. And so I can measure that in the field. And what does that look like? Well, this diagram on the right here is showing that how do we figure out the strike is we see this tilted bed at the surface. We're going to imagine a horizontal line, like the surface of the earth. And where those two planes intersect, a line is formed. And then we want to measure that line with our compass and figure out what direction it is going. And so we can be general and say it's striking to the north or to the northeast, or we could be very specific and say it's not just striking northeast, but it's striking north 30 degrees to the east. And this would be an exact orientation of that line that we're calling the strike. Now there is another YouTube video that I put in the lecture material that goes into depth about how to take a strike and dip. Now of course we're not going to do this because I won't see you, but it's useful I think to understand the concept. The big thing is you want to be able to understand how to read this symbol. And once again the lab is going to focus on this a little bit, but even in some of the lecture stuff and the quizzes we want you to be able to look at, and even the homework, a strike and dip symbol, know what it is, and then know how to read it, because this is going to give us an indication into what type of structures that we have. The dip part of the measurement is just basically how steep is this. So you could see from this image on the left here, we could measure how steep this is from the horizontal. So a line going across the image like this, we would just measure how much it has changed. And so on this diagram, you can see it's this angle here that we can measure. And we have a compass that can do that for us. As geologists, you can measure that in the field. And so if we wanted to know how much it's tilted, or in this case dipping, we can measure that, right? We would measure this angle. That's the number that you see right here. You're telling the reader, somebody who's looking at a geologic map, that if this symbol is on the map, it's telling you that the beds are no longer horizontal and there's some tilt there. And so here it's telling you the amount that it's tilted. It is 30 degrees, right, from the horizontal. The bigger the number, the steeper the tilt, all the way up till it's vertical, which would be a 90-degree tilt, right? All right, so just a couple images to show you along the way that are trying to reinforce this idea of strike and dip, because it can be a weird concept. Even weirder because we're trying to do it on a computer instead of actually showing you in the field. But the idea is that we're measuring for the strike this line. This line is formed by my tilted bed and a horizontal surface. The surface of the earth can be that, or a body of water because it would lay horizontal. So this line here that's formed by the intersection is the strike direction. And all I'm doing is taking my compass and measuring that direction, writing it down, telling someone, hey, this is the direction that line is going. And then I'm going to measure how steep the layers are tilted. I'm going to write that down, put that in my symbol, put it on my map, and then hopefully that'll be some information for the reader of the map to know, oh, these rocks have been tilted, oh, and they're tilted this way, and that can help me figure out the structure that I have. Okay, and so this might, once again, just some images to help you see that you could see that these layers here by the coast are tilted, so we know something's occurred here, fault, fold, not sure yet, but where the tilted layer meets the flat surface of the earth, a line is formed. We just bust out our compass, point it in that direction, and read what the compass is telling us for direction. And then of course I could set my compass on this little tilted layer here and figure out how much it is tilted. Right? Once again, some more images of tilted layers, right? Tilted layer intersecting a flat surface, this case the beach, that's the line. I would just tell you what direction that line is going, and voila, we would have the strike. Measure how much it's tilted, we would have the dip. Just like that. Or like that. So what do we use to measure that? So officially we use what's called a Brunton compass. So here's a couple images of what a Brunton compass is. It's a little more sophisticated than your average compass for sure, but it still is something that is going to measure and point in the direction. So what you're doing is you're taking this little pointer here and you're going to line it up with the strike direction. And then the white little indicator on my compass here is going to point somewhere, and then I can either tell you it's northwest, or I could tell you it's 30 degrees, 40, 50, 100, 180, 270, all the way up to 340, and that would also tell me a direction. Instead of either it's north 10 west, it might be 350 degrees. Those would be the same. But because this has lots of cool features to it, it's got a level bubble, so I can hold it level, so when I'm measuring my compass direction, it's accurate. It also has this level bubble, which allows me to figure out the tilt of the beds. So of course, once again, there's a video that shows you how to do that. In theory, we're not going to do that, obviously, but if you're interested in learning a little more about how you would take a strike and dip, you want to go ahead and watch that video. The other thing to be aware of is the symbol that we draw on the map is always going to look like this. There will be a long line that represents the direction of strike. So remember, when we look at a map, a geologic map, a topo map, north is to the top of the page. And so if I was to draw a strike line on my map, I want to draw it correctly, referencing north to the top of my page. If I measured a strike, let's say is north 30 degrees to the east, I'm actually going to have to draw that line oriented not straight up and down, due north, but 30 degrees toward the east of my map. And so of course I can do that with a protractor, which is how you would accurately draw the strike direction on every map. This is why I don't have to write it down and tell you what it is I'm going to show you. On my map, I'm going to place it on there in the correct compass direction. And that way, if you really wanted to know what it was when you were looking at a map, you could break out a protractor and measure it, and then you would know the direction that it is striking. The dip is represented by this little shorter line that is always drawn perpendicular to the strike, because the strike and dip are always perpendicular to each other. So I'm always going to draw this perpendicular. It's going to be a little shorter. And the reason I have to draw it is, of course, for every strike, I have two directions of dip. It could dip this way to the top in this example, or to the bottom here. So I have to tell you which way it's dipping. And then I am going to write a number here that represents how much it's dipping. So strike and dip symbols always look like this. A long line like this that is oriented in the correct strike direction. A shorter line that's 90 degrees, right, perpendicular to this larger line. You never tilt it. It's not representing visually how much it's tilting. It's just indicating which side, right, the two choices I have. This number is telling me how much it is tilted. Okay, so we want to be able to understand what that symbol means when we look at it on a map. Once again, in lab, you'll have some practice with that. Okay, and so just as an example, some of the things you're going to see when we look at the homeworks and when you look at lab is, of course, I can't show you every picture. We can't go outside. And so sometimes what you'll see in a map view, remember, map view is what looking down on the earth looks like. You would see on a map a strike and dip symbol like this. What is this telling you? Right? This is telling you that this is the strike direction, right, where the tilted layers intersected the flat surface of the earth. The direction it is tilted. And so over here, my layers are tilted to the right. On this side, my layers are tilted to the left. When you see this in cross-sectional view, this is what you want to imagine. The layers are no longer horizontal. They have a dip. Which way? Well, they're dipping toward this side, and over here they're dipping toward this side. If you like, there's a middle here, a center. They're dipping away from the center. And so this is the shape that is formed by the tilted layers that have these strikes and dips. And so we'll come to this in just a minute, but we call this structure, it's a fold structure, we would call it an anticline. And so based on the map view, you should be able to figure that out. Based on the cross-sectional view, you can figure that out. And then of course trying to combine them for you so you can kind of see how they relate to each other. This is how and why we want to use strike and dip symbols. I don't always have a side view. I don't know what's going on down here because I don't have a lovely road cut to show me. I might only have the surface of the earth. And so as I walk along the surface and see the tilted beds and can measure them, I can use that information to infer what's happening at depth. And then I would make a cross section. And you've seen some cross sections and we've done labs previously. This is how the cross sections are developed, is that we use information on the surface to help us kind of infer what's happening at depth. All right. I'm going to take a little break here and then we'll jump back to this really quickly, kind of go through the folds part, okay?